Hi everyone. So, like I said, last time in the last lecture, we talked about the second derivative, came up with the notation, and we did one example. And I let you do some practice problems on your own. So, sorry, the worked examples video, and then you did some practice problems on your own, hopefully. Okay. So, let's move on. And as promised, we are now going to talk about what the implications are of the second derivative. Like why do we care? Why do we go as far as doing that process again? So in order to understand that, I'm going to first of all just clear out a few things. These are stuff you already know. I'm just going to write it out so it's pretty clear. Okay. The derivative, okay, what does that tell us about the function? Okay. It gives us the rate of change. Rate of change of y. Okay. It gives us the slope of the tangent to y. To y, or any function, okay? Very simple. What we learned after that was if dy on dx is positive, if the derivative is positive, function is increasing. Okay, if dy on dx is negative, function is decreasing, okay? Again, we already know all of this, just writing it out because we're going to refer back to this when we start talking about the second derivative. Okay, so since a derivative of a function tells you the rate of change of the function, right? Wouldn't it make sense to say that the second derivative tells you the rate of change of the first derivative, right? It may seem a bit intuitive or a bit, what is he talking about? Just give it a thought, okay? Let it sink in. Second derivative shows the rate of change of the first derivative, okay? Because it is the derivative. That's what its job is, to tell you the rate of change of the previous function, okay? There we go. So let me just write that down, that the second derivative, use the shorthand, gives rate of change of first derivative, okay? Very simple, very straightforward. Now, what does the first derivative tell you? This should be a much easier question, okay? It gives you the slope of the tangent, okay? It also gives you the rate of change, but it gives you also the slope of the tangent, okay? So that's one thing. It gives you the rate of change of okay? So it gives you the rate of change of the derivative. Before we include that tangent part, I just want to give a quick example I just thought of. If, for example, your y is your distance, the rate of change of distance with time is speed, okay? So that would be your first derivative. And then the rate of change of speed is acceleration, okay? How your speed is changing. So that is an example of the rate of change of a derivative, okay? So now we include this tangent part, and we can literally just write it as, well, this gives you the tangent, okay? So I can say, slope of tangent, then this gives us, the second derivative gives rate of change of slope of tangent, okay? I've literally just replaced derivative with the slope of tangent because that is what it gives, okay? So the second derivative gives you the rate of change of the slope of the tangent. Very straightforward, okay? It's not as simple, okay? It's a bit confusing, but give it a thought, okay? Give it a second and it will sink in, okay? So it gives you the rate of change of the slope of the tangent. Now that that's clear, we know that if a derivative is positive, the function it came from is increasing, okay? So if your second derivative is positive, that means your dy on dx is increasing, right? Therefore, the slope of the tangent, again, literally all I did was replace dy on dx with the slope of the tangent, is increasing. Okay, and now that we have talked about a tangent, it's a good place to start including diagrams. Okay, so for example, if you have a slope that is very negative, like a tangent with a very negative slope, all right, what is happening if your second derivative is positive? What is happening is your slope is getting less and less negative and then increasing to get more and more positive. Okay, so if I connect the dots, literally just connect the dots, this is what our function looks like. Okay, and these are the tangents to the function. Okay, these are all tangents that are getting less or more and more positive. They're increasing. Okay, so I'll just draw the function without all the tangents as well, just so it's clear to see. That is what our function looks like. Okay, similarly, if your second derivative is negative, okay, what is going to happen? The slope of the tangent is going to be decreasing. Okay, slope is decreasing. And what is that going to look like? It's going to look like this. If you have a positive slope, it's going to get less positive, 0, and then negative, and then more negative. Okay, and your function is going to look, actually this time I'm not going to make that mistake. I'm going to go with a different color. Your function is going to look a lot like this. Okay, this is a function whose second derivative is negative. Okay, let me again draw that so that you can clearly see the picture. Okay, now that is what the second derivative tells you. It tells you what the slope is doing. Okay, and this then tells us kind of like the shape of the function. We've said shape. It's like it's this kind of shape. We're gonna get more formal now. Okay, we call this and this shape a type of concavity. Okay, concavity. Okay, both of these sort of shapes, structures are called concavities. Okay, this is a concave up function. Okay, this function is concave up. Why is it concave up? Because the slope of the tangent is going up. It is increasing. So concave up. Similarly, this one is concave down. Okay, because second derivative is going down. Okay, again, everything kind of flows into the other. So now that is our final conclusion that if the second derivative is positive, the function is concave up, which means that the slope of the tangent is increasing. If the second derivative is negative, the function is concave down, which means the slope of the tangent is decreasing. Great. So, like we did with the derivatives, we know what it does when it's positive. We know when it's done, what happens when it's negative. But what about when it is at 0? At positive it's concave up, negative is concave down. What about when the second derivative is 0? Is it a concave middle? Is it a concave neutral? That is kind of actually what happens actually. When the second derivative is 0, that means that the function has no concavity. That is such a hard word. Function has no concavity at that point where the second derivative is 0. Let's try that again. Y has no concavity. Okay. So points like, so if you have, for example, this linear function, okay, which is y equals mx plus c, we can quickly just find the second derivative, dy on dx, dy, not a d scribble, dy on dx is equal to m, and then d2y dx2 second derivative is equal to 0. Okay, so the derivative is 0, and at all points, the function has no concavity. Again, it's hard one, allow it. So the function has no concavity. Concavity, and you can see that clearly because the slope at O point is constant. Slope is not changing. Okay, so no concavity. Great. Now, another cool thing about this is that when if the second derivative is 0 at a point, before and after those points, it's not going to be 0. Okay? If it is only at that singular point, in that vicinity, okay, if it is 0 here at this point, sorry, I've drawn it incorrectly. So yes, I am doing a sign diagram again, f double dash of x, or this, as we've been doing this whole time. Okay? So if at a point it is 0, here it is going to have some sign. They're not going to be 0. Okay? Something like that, or positive, whatever. All right? And based on that, you can tell about the function. Again, all right? So if you have like a positive and a positive, this is what the function would look like. It is a concave up function. Okay, it's a concave up function. Then it has no concavity, and it stays a concave up function. Okay, so here, no concavity. If you have something like this, where this happens, then you have a concave up function, okay, which then has no concavity at one point, and then a concave down function. Okay, okay. It doesn't necessarily need to look like that. Maybe it's like, maybe it is like this, and then at this point it has no concavity, and then it starts to become concave down. Okay. Next one, just an opposite one of that. It's concave down, turns into concave up, and then concave down, turns into concave up. Okay. Now you may have noticed these. Okay, these are non-stationary inflection points, and very, very soon you're going to learn why they're called inflection points, like I promised. Okay. One more. The negative and negatives. Okay. This is just something like this, or something like that. Okay. Not a very interesting one. No concavity, but it's important to note this. Okay. So now we know that when the second derivative is 0, you have points without any concavity. Okay. Now those points that do not have any concavity play an important role in some cases. They play important role in the cases when the concavity changes. So in these two cases, okay, the concavity is changing from being up concave to down concave, okay, and down to up, okay. In both of those cases, you are changing the concavity. Those points are called inflection points. Okay, so inflection points, concavity changes. Okay, now these types of points, both of these, okay, these are called stationary inflection points, and we know why, because the function is stationary. Okay. Okay, fairly straightforward. These types, because they are not stationary, they are very unoriginally named non-stationary points. Okay, because the function at those points of inflection are non-stationary. Okay. And there you have it. Okay, that is all you need to know about the second derivative. This is the geometrical applications of it. Oh, by the way, I forgot to mention one more thing. If you look at these two functions, just really quickly, bear with me. If you look at these two functions, you would know that if in this region, okay, if in this region of the function, you find a turning point. You find a point where the first derivative is 0. You find a critical point. Now, before, when we found those critical points, in order to find whether it's a local minimum or local maximum, we would do that whole sign diagram stuff. Now, you can just see if the second derivative is positive or negative. Okay? Because if the second derivative is positive, right? If the second derivative is positive, your function, your tangent is increasing. Okay? Say this is the point you found, critical point, and you know it's a turning point, okay, because there's a different signs on each side. Because the tangent is increasing as you go from left to right, okay, here it would have gone like this. It would have been a very negative one, and then less negative, and then minimum negativity, and then from that point going up, okay, for the slope. This critical point, you would know, you would be able to see that this is a local min. Okay, so if the second derivative is positive, the function is concave up, okay, and you find a critical point, that critical point becomes a local min, okay. Similarly, if the second derivative is negative, at that point, the function is concave down, right? So the critical point is then a local max, okay. Another thing, one last thing, I promise, is that at these points, okay, another thing to note is that at these points, here before that, the tangent is increasing, okay. Look at this one, for example. Tangent is increasing, gets increasing, more and more increasing, till it reaches this point, and from that point onwards, it starts decreasing, okay. So if I kind of like visualize the tangent, okay, the value of the tangent goes up, reaches a point, this point here, and then starts decreasing, the slope of the tangent, okay. So you can clearly see, right, even when I visualize it, that this point here, at this point here, the slope is at a maximum, okay. Similarly, here, okay, it goes like this, it goes less negative, reaches 0, and then starts getting negative again. This one is more obvious that this one is also a local max. Oh, sorry, not a local max. It's a max for the slope. Max for slope. Okay, this is where the slope again reaches its maximum value. In this case, 0. Okay. Similarly, if we look at these two, it has the slope is very positive, up, and then it starts to get less and less positive. It becomes negative until it reaches this point, and then starts getting positive again. It starts increasing again. So what was I saying? Less negative? I meant as you go from left to right, from here to here, it gets more and more negative. Okay. So as it gets more and more negative, at this point, it starts to get positive again. It becomes the tangent starts to increase. So at this point, the same reasoning as this one, the slope is minimized because slope is decreasing and then starts increasing beyond this point. Okay. Similarly here, you have a big positive slope, approaches 0, and then starts increasing again. So 0 is your minimum. Okay. Slope. Okay. Let me just write that a little better. Minimum. Cool. There you have it. All right. So inflection points, concavity changes. All right. Minimum or maximum for slope. All right. And that is, I believe, it. It also, the second derivative helps you with local mins and max, but that's okay. That is all that you need to know for the second derivative. This time, I promise. Okay. Yeah, but it is a lot. Okay, it is a lot to take in, and don't feel too overwhelmed if you feel like, oh my god, there's so much. But it happens. Okay, just give it some time. Go over this again if you need to. But as I always say, do practice questions. Okay, that's what's going to help you the most.